Hello and welcome in a new video. We will solve now exercise 7, dealing with the normal reaction. So the question is, when do we have contact and when the object loses contact with the support? So let's read the exercise. A boy is initially seated on the top of a hemispherical ice mound of radius r equal 13.8 meters. So we have a boy sitting on this hemispherical ice. He was at point A at t0. Then he begins to slide down the ice with a negligible initial speed. See the figure. So at A, his speed was negligible, so he started from rest. He slides down the ice, and then he will reach a certain point at which he will lose contact with the hemisphere. So the point at which he is losing the contact is B. Approximate the ice as being frictionless. At what height does the boy lose contact with the ice? So we need to find the height at which the boy loses contact with the ice. So we want to find HB. So A designates the initial point, the starting point, and B designates the final position of the boy on the sphere where he will lose contact with the ice. So when we say a boy loses contact with the ice, this means that we don't have anymore any normal reaction. So this exercise deals with the normal reaction. So at the first step, we have to find the normal reaction and we have to put it as equal to 0, or we can write that the normal reaction should be less than or equal to 0. So we can find the height at which the boy loses contact with the ice. So let's find the normal reaction. And to find this normal reaction, we have to apply the fundamental relation of dynamics on the boy. So we have two forces acting on the boy. We have the weight of the boy, mg, vertical downward, and we have the normal reaction of the ice. It's perpendicular to the hemispherical ice. So we can write mg plus n equal ma. Now to find the normal reaction, we have to project this equation on the normal unit vector. But before, let's define the angle theta as the angle between the position vector OB and the horizontal axis, the x-axis. So this is theta. So now we want to project mg plus n equal ma on the normal unit vector. The normal unit vector is a unit vector which is directed toward the center of the circle. So it's directed towards O. It has this direction. Now the projection of mg along the normal unit vector will give us mg times cosine of this angle. And this angle, let's say it's alpha, it's complementary to theta. So this will give us mg sine theta. Now let's project n on the normal unit vector. Now I will draw the normal unit vector. It's directed, as I said, toward the center of the circle. Now the projection of the normal reaction on the normal unit vector will give minus n. And the projection of MA on the normal unit vector will give MAN, and AN is equal to V squared over R. Okay, so let's put N equal 0. So we will have mg sine theta equal mv squared over R. We can simplify with m, and we will obtain V squared equal GR sine theta. So at point B, V squared is equal to GR sine theta, where the point B is the point of losing contact between the boy and the ice. But what is VB? Or can we find a relationship between VB and the height at B? So let's make now, let's use the conservation of the mechanical energy between A and B. Since we don't have any friction, so here they said that the ice is frictionless, so we can use the conservation of the mechanical energy between A and B to find the relationship between VB and HB, where HB is equal to R sine theta. So the mechanical energy at point A is equal to the potential energy, the gravitational potential energy, which is equal to mg times HA, where HA is equal to the radius of the hemisphere. Now the kinetic energy at point A is 0 because the boy started from rest at A, so the mechanical energy at point A is only mgr, and this is equal to the mechanical energy at point B. So we have the potential energy and the kinetic energy. The kinetic energy is half mvb squared, and the potential energy is equal to mghb, where hb is equal to r sine theta. Let's replace vb here with its expression already found from the fundamental relation of dynamics, and therefore we will obtain that mgr is equal to mgr sine theta plus half mgr sine theta. So here we have mgr sine theta parenthesis 1 plus half. This will give us mgr sine theta times 3 over 2, and therefore we can find that sine theta is equal to 2 over 3. Now hb is equal to r sine theta, and therefore we can deduce that hb is equal to 2 over 3r, and this is the height at which the boy loses contact with the ice. So in this exercise, we use the fundamental relation of dynamics to find the expression of the normal reaction, and then since we don't have any contact at point B, we put that n is equal to 0. We deduced the expression of the speed at point B, and then we found a relationship between V and theta, or it's the relationship between V and HB. And this is the relationship between VB and HB. So HB is R sine theta, using the conservation of the mechanical energy. So we are able to use the conservation of the mechanical energy because they said that the ice is frictionless. Finally, we deduced the maximum height at point B.